Welcome, everyone. Today we're starting our chapter on joints, also known as articulations. In this chapter, we'll explore how bones connect with one another and how these connections allow for the wide variety of movements we see in the human body, from the flexibility of your fingers to the stability of your skull. Joints are essential not only for mobility, but also for stability and support. We'll look at how joints are classified, how they function, and the anatomical features that help protect and stabilize them. By the end of this unit, you'll be able to understand the difference between a freely movable joint like the shoulder and an immovable one like the sutures in your skull. Let's dive into the structure and function of joints and see how form truly follows function in the human body. Let's begin by reviewing the learning objectives for Chapter 7. These will guide what we focus on in today's lecture and throughout the chapter. First, we'll classify joints in two main ways: functionally, which refers to how much movement a joint allows, and structurally, which refers to what kind of tissue connects the bones and whether a cavity is present. Next, we'll explore the three main structural types of joints: fibrous, cartilaginous, and synovial, along with key examples and their defining features. Then we'll move into how the body moves at the joints. You'll learn to identify different types of body movements such as flexion, extension, rotation, and more. We'll also examine several specific joints, like the shoulder, knee, and hip, and see how their structure allows particular types of movement. Finally, we'll briefly touch on how joints develop embryologically and how they change over time. By the end of the chapter, you should be able to describe joints both structurally and functionally, relate structure to movement, and recognize how stability and mobility are balanced throughout the body. Now let's define what a joint is and why it's so important. A joint, also known as an articulation, is the point of contact between two or more bones. In anatomy, this concept is fundamental because joints are what allow our bodies to move, and they also help keep our skeletons structurally sound. Interestingly, almost every bone in the human body is connected to another bone through a joint. The exception is the hyoid bone, which is found in the neck and supports the tongue. It doesn't form a traditional joint with any other bone, which makes it unique. Joints serve two primary roles. First, they enable movement, which is especially obvious in places like the elbow, shoulder, or knee. Second, some joints are designed for stability, like the sutures in the skull, which lock bones together and prevent movement. It's also helpful to think of joints in terms of how much movement they allow. Freely movable joints like those in your limbs are called diarthroses. Slightly movable joints, like between the vertebrae, are amphiarthroses. And immovable joints, like those in the skull, are called synarthroses. As we move through this chapter, you'll see how structure directly impacts function. The way a joint is built will determine how it moves, or whether it moves at all. This slide focuses on one of the key concepts in joint anatomy: the trade-off between mobility and stability. Joints need to strike a balance between these two properties depending on their function and location. For example, the shoulder joint is one of the most mobile joints in the body, allowing for a wide range of motion: rotation, lifting, reaching. But because of that mobility, it is also less stable, and that's why shoulder dislocations are relatively common. On the other hand, joints like the sutures of the skull are extremely stable. They lock bones together tightly and protect the brain. But that stability comes at the cost of no movement at all. That's completely fine for the skull because its job is protection, not movement. So the important takeaway here is this: a joint can't be both highly mobile and highly stable at the same time. The body adapts each joint based on what it needs to do. You'll see this principle over and over again as we go through specific examples, like the hip joint, which strikes more of a balance, offering both strength and some mobility. This inverse relationship is a guiding principle of joint anatomy and function. Joints are broadly classified in two ways: structurally and functionally. The structural classification looks at how bones are physically connected, whether by fibrous connective tissue, cartilage, or enclosed in a fluid-filled cavity. This gives us three types: fibrous, cartilaginous, and synovial joints. The functional classification focuses on how much movement the joint allows. We categorize joints as synarthroses, immobile, amphiarthroses, slightly movable, or diarthroses, freely movable. You'll notice that these two classification systems often overlap, So, for instance, fibrous joints are typically synarthroses. We'll walk through each category in the coming slide. This slide introduces the three main structural types of joints, which are classified based on what connects the bones and whether or not there is a joint cavity between them. Let's start with fibrous joints. These are held together by dense, regular connective tissue and do not have a joint cavity. That means the bones are in direct contact or very closely bound. These joints are mostly immobile, which is why they're found in places where protection and stability are important, like the sutures of the skull, which protect the brain. Next, we have cartilaginous joints. These are united by cartilage, either hyaline cartilage, which is smooth and found at growth plates, or fibrocartilage, which is tougher and found in places like the pubic symphysis or intervertebral discs. Like fibrous joints, cartilaginous joints lack a cavity. They typically allow for slight movement, making them structurally stable but still somewhat flexible. Finally, the most familiar and functionally versatile, synovial joints. These joints are defined by the presence of a joint cavity filled with synovial fluid, which acts as a lubricant. The bones in a synovial joint don't touch directly. They articulate within this cavity, which allows for free movement. Every major movable joint in your body, your knees, elbows, shoulders, fingers, is a synovial joint. To summarize, fibrous equals tightly bound immobile, cartilaginous equals slightly movable, and synovial equals freely movable. These categories help explain why certain joints are capable of movement and others are not, because it's all in the structure.
Let's begin with fibrous joints, the simplest structurally. These joints involve bones that are directly connected by dense, regular connective tissue, the kind that's very strong and collagen-rich. There is no joint cavity in fibrous joints, and because of their tight fit, they're usually immobile, what we call synarthrotic. However, some types can allow for a small degree of movement. There are three subtypes. Sutures, which are found only in the skull. These interlocking joints stabilize the cranium and protect the brain. In newborns, they are wide and soft, called fontanelles, but they ossify over time. Syndesmoses are found between long bones, like the radius and ulna or tibia and fibula, connected by ligaments or interosseous membranes. These allow slight movement, so they're sometimes functionally considered amphiarthroses. Gomphoses are peg and socket joints, where teeth fit into their bony sockets and are held in place by the periodontal ligament. These are immovable and are a great example of how specialized. Now let's move on to cartilaginous joints. In these joints, bones are joined together by cartilage, not connective tissue. Like fibrous joints, there is no joint cavity, so the bones are still fairly close together. These joints allow limited movement, so they're usually classified as amphiarthroses. There are two types: synchondrosis, where bones are united by hyaline cartilage. These can be temporary, like the epiphyseal plates in growing bones, or permanent, like the connection between the first rib and the sternum. Symphyses, where bones are joined by fibrocartilage, a tougher, more fibrous cartilage that can resist tension and compression. Examples include the intervertebral discs and the pubic symphysis, both of which allow some movement while maintaining structural integrity. These joints are adapted for strength with flexibility, making them ideal for regions of the body where shock absorption and stability are both necessary. Finally, we have synovial joints, the most complex and most common type in the body. In these joints, the articulating bones are not directly connected. Instead, they are enclosed in a joint capsule with a synovial cavity filled with synovial fluid. This fluid lubricates the joint, reduces friction, and allows for smooth movement. These joints are freely movable, which means they are functionally classified as diarthroses. Synovial joints include the shoulder and hip, ball and socket joints, the elbow and knee, hinge joints, the wrist, ankle, and fingers. These joints also have additional features like ligaments, tendons, articular cartilage, and sometimes menisci or bursae, all working together to provide mobility, support, and shock absorption. You'll see these joints in great detail later, especially when we study joint movement types and specific examples. Functional classification answers the question,
How much movement does this joint allow? A synarthrosis is an immovable joint. These are often found where bones need to stay firmly in place to protect organs, like the sutures in the skull. An amphiarthrosis allows limited movement. Examples include the joints between vertebrae or the pubic symphysis, which offers flexibility during childbirth. A diarthrosis is a freely movable joint, and all diarthroses are synovial joints. These are the joints in your limbs, your elbows, knees, hips, that let you move in multiple directions. The location of each joint type reflects its role, whether stability or mobility is more important in that region. A synarthrosis is a joint that allows for no movement. It's completely immobile. These joints are typically found in parts of the skeleton where stability and protection are the priority rather than motion. Functionally, synarthroses are very strong because the bones are tightly joined. These joints can be either fibrous, like sutures in the skull or gomphoses in the jaw, or cartilaginous, like the epiphyseal plate in a growing bone. For example, the cranial sutures fuse the bones of the skull to form a protective case for the brain. The gomphosis holds the tooth root firmly in place in the jawbone. Even the growth plate in a child's long bones acts as a temporary, non-movable joint until it ossifies and the bone stops growing. The key function of synarthroses is strength through immobility. An amphiarthrosis is a slightly movable joint. These joints allow for limited flexibility while still maintaining structural support. You'll often find them in areas that need to absorb stress or allow for small movements that add up across a region of the body. These joints can also be either fibrous or cartilaginous. A fibrous example is the distal tibiofibular joint, which provides a bit of give to support ankle motion. Cartilaginous examples include the intervertebral discs, which allow for slight flexing and bending of the spine, and the pubic symphysis, which is especially important in childbirth when it slightly loosens. Amphiarthroses are great examples of how the body balances stability and motion. They move just enough to be functional, but are still strong and supportive. Lastly, we have diarthroses. These are freely movable joints, and they're responsible for nearly all of our conscious body movement. All diarthroses are structurally synovial joints. That means they have a fluid-filled joint cavity, articular cartilage, and often extra features like ligaments or bursae for support and motion. Diarthroses are classified further based on how many axes of movement they allow. Uniaxial joints move in one plane, like the elbow, which flexes and extends. Biaxial joints move in two planes, like the knuckles, which allow both flexion-extension and abduction-adduction. Multiaxial joints move in all three planes, like the shoulder or hip, which allow you to swing your arm in a full circle or rotate your leg. These joints provide the most mobility, but they also require supporting structures to maintain stability. We'll examine those structures more closely when we dive into synovial joint anatomy. Let's begin our exploration of synovial joints, the most abundant and functionally versatile type of joint in the body. These joints are what we rely on for most of our everyday movements: walking, writing, turning your head, picking up objects, all made possible by synovial joints. Structurally, what sets them apart is the presence of a synovial cavity, a space filled with lubricating fluid that separates the bones and allows them to glide past each other with minimal friction. Because of this design, all synovial joints are classified functionally as diarthroses, which means they allow free movement. But not all synovial joints move the same way. Some rotate, others glide, some hinge open and closed. Importantly, the bones at these joints are not directly connected by cartilage or fibrous tissue. Instead, they're housed inside a capsule and protected by supporting structures like ligaments, tendons, cartilage, and synovial fluid. This structure allows for both mobility and protection. As we go deeper, we'll look at the joint's anatomy, supporting structures, and the 6 different types of synovial joints based on how the bones articulate and move. Let's take a closer look at the key structural features that make synovial joints unique and functional. First, at the core of every synovial joint is the joint cavity, a small, enclosed space that allows the bones to move freely.
This cavity is filled with synovial fluid, which acts like motor oil for your joints, reducing friction and allowing smooth motion. This cavity is surrounded by the articular capsule, a two-layered structure. The outer fibrous layer is made of dense, irregular connective tissue. It blends with the periosteum of each bone and gives the joint strength and resistance to dislocation. The inner synovial membrane produces synovial fluid, a thick, slippery fluid that lubricates the joint and nourishes the articular cartilage, which lacks blood vessels. Speaking of cartilage, the articular cartilage is a layer of hyaline cartilage that covers the ends of each bone at the joint. It's not fused, like in cartilaginous joints. Instead, it's like a smooth, protective cap. It absorbs shock and prevents the bones from grinding directly against each other. Together, these features allow the joint to move freely and efficiently, making synovial joints perfect for the dynamic activities our bodies perform. Now that we've covered the basic anatomy of synovial joints, let's talk about the supporting structures that stabilize these joints and protect them from damage. First, we have ligaments. These are strong bands of dense, regular connective tissue that connect bone to bone. They limit or control the joint's range of motion to prevent hyperextension, dislocation, or abnormal movement. Ligaments can be extracapsular, located outside the joint capsule. Capsular, thickened parts of the capsule itself. Intercapsular, found inside the joint capsule, like the ACL in the knee. Next, we have tendons, which connect muscles to bones. They play a huge role in joint stability, especially during movement. When a muscle contracts, its tendon can act like a dynamic ligament, reinforcing the joint. This is critical in joints like the shoulder, where the ligaments alone are relatively weak. Some joints, especially the knee and jaw, have special fibrocartilage structures called menisci, or articular discs. These help improve the fit between bones, provide shock absorption, and guide movement. A classic example is the meniscus in the knee, which helps the round femur fit better with the flat tibia. Finally, fat pads are found in some joints and serve as cushions. They help absorb pressure and fill spaces as the joint moves and changes shape. Together, these structures ensure that synovial joints are not only mobile, but also strong and protected, even under constant stress. Now let's look at two important friction-reducing structures found around synovial joints, bursae and tendon sheaths. A bursa is a small, fluid-filled sac lined with synovial membrane and filled with synovial fluid. Its main function is to reduce friction where tissues like skin, tendons, or muscles might rub over bones. Depending on their location, bursae are named differently. A subcutaneous bursa is found between skin and bone, like the prepatellar bursa over the kneecap. A submuscular bursa is between a muscle and a bone, or between two muscles. One example is the trochanteric bursa of the hip. A subtendinous bursa lies between a tendon and a bone, like the subacromial bursa in the shoulder, which protects the supraspinatus tendon. A tendon sheath is basically an elongated bursa that wraps around a tendon, especially in areas where the tendon crosses a joint or moves a lot, like in the wrists and ankles. It's like a lubricated sleeve that ensures smooth tendon movement without friction or irritation. Together, bursae and tendon sheaths help protect your joints from wear and tear, especially in high-motion areas like the shoulders, elbows, and knees. When these structures become inflamed, it can lead to a painful condition called bursitis. Now that we've covered the structure and support systems of synovial joints, let's explore the 6 types of synovial joints. These types are based on the shape of the articulating surfaces and the direction and number of planes of movement they allow. In anatomy, we often describe joint movement in terms of 3 anatomical planes: sagittal plane, flexion, extension; frontal plane, abduction, adduction; transverse plane, rotation. Depending on the shape of the bones at a joint, movement can occur in 1, uniaxial, 2, biaxial, or 3, multiaxial planes. For example, a hinge joint like the elbow only allows movement in one direction, so it's uniaxial. A condylar joint, like the wrist, allows movement in two directions, so it's biaxial. And a ball and socket joint, like the shoulder, allows movement in all directions, multiaxial. In the next slides, we'll go through each type individually, look at their structure, and see examples from the human body. Let's begin our look at the 6 types of synovial joints with the one that offers the greatest freedom of movement, the ball and socket joint. In this joint, a rounded, ball-shaped head of one bone fits into the cup-like socket of another. This anatomical design allows for multi-axial movement, meaning the joint can move in all 3 anatomical planes: sagittal, flexion and extension; frontal, abduction and adduction; transverse, rotation. You'll find ball and socket joints in just 2 locations in the human body: the shoulder joint, where the head of the humerus fits into the glenoid cavity of the scapula. This joint has the widest range of motion of any joint, but it's also the least stable, making it prone to dislocations. The hip joint, where the head of the femur fits into the deep acetabulum of the pelvic bone. While not as mobile as the shoulder, the hip is much more stable, designed for weight-bearing and support. These joints are essential for activities like throwing, running, climbing, and turning your leg or arm in all directions. Next, we have the hinge joint, one of the most mechanically straightforward synovial joints. Hinge joints are uniaxial, meaning they allow movement in only one plane, typically the sagittal plane, so the motions are limited to flexion and extension, much like the action of a door hinge. Structurally, one bone has a convex surface that fits snugly into the concave surface of another. This tight articulation provides good stability and a controlled range of movement. Common examples include the elbow joint, where the trochlea of the humerus fits into the trochlear notch of the ulna; the knee joint, which functions as a modified hinge, although it allows for a small degree of rotation when flexed; the interphalangeal joints of the fingers and toes, which allow you to bend and straighten your digits. Although hinge joints don't allow for much complexity in movement, their strength and simplicity make them perfect for providing precise, controlled motion in the limbs. Let's move on to pivot joints, another type of uniaxial synovial joint. These joints allow for rotational movement around a single axis, typically in the transverse plane. Structurally, they feature a rounded or pointed surface of one bone that fits into a ring formed by another bone and a ligament. There are 2 classic examples: the atlantoaxial joint, located between the first, C1, and second, C2 cervical vertebrae. Here, the dens, odontoid process, of the axis, C2, pivots within a ring formed by the atlas, C1. This joint allows you to shake your head, no. The proximal radio-ulnar joint, where the head of the radius rotates against the ulna, enabling pronation and supination of the forearm, turning your palm up and down. Though the range of motion is limited to one movement, rotation, pivot joints are essential for key head and arm movements and play an important role in everyday actions like turning a doorknob or looking over your shoulder. Now let's take a look at plane joints, also known as gliding joints. These joints are formed between bones that have flat or slightly curved surfaces. Unlike hinge or pivot joints, there's no rounding or concavity, just smooth, nearly planar surfaces that allow bones to slide past each other. Plane joints are often considered multiaxial because the bones can move in multiple directions: forward, backward, side to side, and a bit of rotation. But in reality, the range of motion is very limited due to surrounding ligaments and neighboring bones. What makes these joints important is that their small, subtle movements can combine to create flexibility in areas like the wrist, foot, and vertebral column. Examples include the intercarpal joints in the wrist and intertarsal joints in the foot, which allow the hand and foot to adapt to shifting surfaces. The acromioclavicular joint, where the clavicle meets the acromion of the scapula. The zygopophyseal joints between the superior and inferior articular processes of vertebrae, which allow for spinal movement. Even though they don't provide dramatic motion, plane joints are crucial for fine adjustments and maintaining flexibility in compact, high-stress areas. Next up are saddle joints, a unique and highly mobile type of biaxial synovial joint. In this joint, both bones have saddle-shaped articulating surfaces. They are concave in one direction and convex in the other, like 2 saddles fitting together at right angles. This shape allows motion in 2 planes: flexion and extension, abduction and adduction.
Because of this configuration, saddle joints offer greater mobility than a typical hinge or condylar joint, while still maintaining stability. The best example is the first carpometacarpal joint, where the trapezium bone of the wrist articulates with the first metacarpal bone of the thumb. This joint enables the thumb to move in multiple directions and to perform opposition, a motion where the thumb can touch the other fingertips. This ability is one of the reasons human hands are so dexterous. Another example is the sternoclavicular joint, where the clavicle meets the manubrium of the sternum. It's classified as a saddle joint because of the way its surfaces interact, allowing movement of the clavicle in two planes, raising or lowering, and moving forward or backward. So although saddle joints are rare, they're incredibly important for functions that require fine motor control and multi-directional movement. Our final type of synovial joint is the condylar joint, also called the condyloid joint. These joints are biaxial, meaning they allow for movement in two planes, typically flexion and extension in the sagittal plane, abduction and adduction in the frontal plane. The articulating surfaces include an oval-shaped condyle, rounded projection, of one bone that fits into a shallow, oval depression of another. Unlike ball and socket joints, condylar joints do not allow rotation because the shape of the surfaces restricts twisting motions. One of the most familiar examples is the metacarpophalangeal joints, your knuckles, where the metacarpal bones of the hand meet the proximal phalanges of the fingers. These joints allow you to bend your fingers and also spread them apart or bring them together. Another important example is the radiocarpal joint, where the radius articulates with the carpal bones of the wrist. This joint allows the hand to move forward and back and side to side, but again, no rotation. So condylar joints offer a nice balance, more movement than a hinge, but less than a ball and socket, making them well suited for joints that require controlled, multi-directional movement.